In this video, we're going to talk about how to solve absolute value inequalities. So suppose we want to solve the inequality absolute value of 3x minus 6 is less than 15. Well, one thing we can never do with an inequality question is simply remove those absolute value brackets and just say 3x minus 6 is less than plus or minus 15. We have to use the interval method. So what we're going to do is we're going to let the interior of the absolute value bracket equal 0 and solve for x. So when we do that, there's only one linear factor in there, and we get x equals 2. So we're going to make a number line, mark the value x equal 2, and draw a line down the middle at x equal 2. I sometimes call that a wall. Okay? Now, for numbers to the left of 2, the value of 3x minus 6 is negative. For instance, if you let x be any number at all less than 2, let's say 1, you would get a negative value. Well, we learned in an earlier presentation that when w is negative, the absolute value of w is negative w. So since 3x minus 6 is negative, the absolute value of 3x minus 6 is negative of 3x minus 6. That's doubly negative, so to speak, making it positive. So what we're really trying to solve on this side of the inequality is negative of round bracket 3x minus 6 round bracket is less than 15. So we've taken the inequality that has the absolute value brackets, the vertical ones, and we've changed it to this inequality, which is true when we're on the left of 2, if x is less than 2. So and then for numbers to the right of 2, when x is greater than 2, the value of 3x minus 6 is positive. In other words, imagine we let x be a number greater than 2. Let's let x be 3. Well, 3 times 3 minus 6 will be a positive value. Well, an earlier rule we learned was that when w is greater than 0, the absolute value of w is w. So on this side of x equal 2, we're going to solve this inequality. So we've got a couple of different inequalities that we're solving, one on one side of 2 and one on the other side of 2. So on the left-hand side of 2, negative bracket 3x minus 6, close bracket less than 15, we end up with negative 3x being less than 9. We divide both sides by negative 3, but of course change the direction of the inequality. We get x greater than negative 3. So we go to the other side of the inequality. We get 3x minus 6 being less than 15, because if you'll recall, we agreed that to the right of 2, the absolute value of 3x minus 6 is equal to 3x minus 6. So we're able to take to the right of 2 this inequality and replace it with that inequality. And then we solve using regular methods. 3x is less than 21, x is less than 7. So what we now do is we, on the basis of the statement x greater than negative 3 to the left of 2, we're only going to include values of x greater than negative 3 that are on the left side of 2, because that x less than 2 is a restriction for that entire part. This entire part of the solution has the restriction on it that x must be less than 2. Okay, so we're going to use the number line as a way to organize our solution. So on the basis of this, we're going to shade in every part of the number line that is greater than negative 3. And you know what? I should not have colored in that circle. My bad. Allow me to just keep an open circle. We're going to shade in every value to the right of 3, but we're going to stop at 2. We're not allowed to go past 2. Okay? Cool. Now, go on the other side. X is less than 7. On the basis of this statement, we're only allowed to include in the solution set values of x less than 7 to the right of 2. So we are going to draw in a 7, and we're going to include values to the left, but they have to be on the right side of 2, like that. So that number line up top acts like a overall solution for us. It's our way of organizing the solution. But as one final task, we might check whether the number on the boundary line makes the original inequality true or false. In other words, let's plug an x value of 2 into this original inequality and see if we should shade in that circle or not. When we let x equal 2, we get the absolute value of 3 times 2 minus 6 is less than 15, which means absolute value of 6 minus 6 is less than 15, ultimately meaning 0 is less than 15. This is true, so we're going to fill in that circle right there. And now we can state our answer in set notation or in interval notation. Okay, how about let's try this inequality. This time we've got two different absolute value quantities. This might get interesting. Well, we're going to set the interior of each of the absolute value brackets to 0, and we're going to solve for x. When 2x plus 10 equals 0, we get x is equal to negative 5. And when 4 minus 2x is 0, we get x is equal to 2. So we're going to build a number line with x equal negative 5 and x equal 2. Now, in that first interval, when x is less than negative 5, for instance, imagine if x was equal to negative 6, you'd have 2 times negative 6 plus 10. That would be negative. So 2x plus 10 would be negative, meaning the absolute value of 2x plus 10 would be negative of 2x plus 10. And then if I let x be a number like negative 6 here, 4 minus 2 times negative 6, I'd actually get a positive number. So since 4 minus 2x is positive, that means the absolute value of 4 minus 2x is 4 minus 2x. So I take each of those two things that I just stated and I sub those in for this inequality. And that's what I did right here. And now I solve using regular grade 10 methods. And we distribute the negative signs in. We get negative 2x minus 10 minus 4 plus 2x is greater than or equal to 8. And when we solve further, we get negative 14 is greater than or equal to 8. Well, that's not true anywhere. Nowhere is that true. So no part of this interval is going to be part of our solution set. And we move on to the next interval. Now, when we're in between negative 5 and 2, for instance, let's say x is equal to 0, the first the interior of the first absolute value is positive, and so we get 2x plus 10 is greater than 0, meaning the absolute value of 2x plus 10 is 2x plus 10. And if continuing by letting x equal 0 just for testing purposes, in this interval I see that 4 minus 2x is also positive, which means that the absolute value of 4 minus 2x will be equal to 4 minus 2x. So I can substitute each of those circled things into that inequality, which I do right here. And I end up with 4x being greater than or equal to 2, which means x is greater than or equal to 1/2. So we're going to shade in this part of the interval where x is greater than or equal to 1/2. And we do that. And remember that 2 acts as a restriction. And sometimes I say, there's a wall there, and you can't go past the wall. Now, to the right of 2, 2x plus 10 is positive. For instance, let x equal 3. Well, 2 times 3 plus 10 is positive. But 4 minus 2x would be negative. 4 minus 2 times 3 is a negative number. So since 2x plus 10 is positive, the absolute value of 2x plus 10 equals 2x plus 10. And since 4 minus 2x is negative, the absolute value of 4 minus 2x is negative of 4 minus 2x. So now instead of solving this, I'm going to solve this. And we go about doing it, and we get 18 is greater than or equal to 8. We literally get 2x plus 10 plus 4 minus 2x is greater than or equal to 8, which means 18 is greater than or equal to 8. What we've got here is a statement that is true no matter what value of x there is. So that means for all values of x in this interval, we're going to shade them in. So we shade in all values of x meeting the restriction that x is greater than 2. Okay, and that's what we've got. Now, as a final thing, we might want to say, should we shade in the -5 and 2 because we're not sure? If you're not sure, plug them in. If I let x equal -5 in the original statement of the inequality, I just continue to evaluate, I end up with 0 minus 14 greater than or equal to 8. Well, is that true? Absolutely not. So -5 is not going to be part of my solution. When I let x equal 2 and I plug a 2 into the original inequality right there, I end up with 14 greater than or equal to 8. Well, that is a true statement. So I'm going to shade in that circle there. And now I can state my final answer. X will be any number greater than or equal to 1/2. That's an element of the reals. Finally, let's do a quadratic inequality. Suppose we say the absolute value of x squared minus 8x plus 7 is greater than or equal to 2. Okay, well, we're going to set the interior of the absolute value brackets equal to 0. That's what we always do, which means x squared minus 8x plus 7 equals 0. We use our quadratic skills and we see x is 1 or x is 7. So we're going to make a number line with 1 and 7 indicated. There we go. Now, when x is less than 1, x squared minus 8x plus 7 is greater than 0. You don't believe me? Take a number less than 1 and plug it in. Let's let x equal 0. 0 squared minus 8 times 0 plus 7 is greater than 0. So that means the absolute value of x squared minus 8x plus 7 is equal to x squared minus 8x plus 7. So in other words, solving this absolute value right here is the same as just solving x squared minus 8x plus 7 is greater than or equal to 2. Okay, well, let's solve it. If x squared minus 8x plus 7 is greater than or equal to 2, then that means x squared minus 8x plus 5 is greater than or equal to 0. Now, what we're going to do with this expression right here is we're going to do interval testing. We've already learned how to do that in previous lessons. We're going to actually build a number line, and we're going to do interval testing to solve where x squared minus 8x plus 5 is greater than or equal to 0. And we're going to do all of that interval testing within this interval of x being less than 1. Interval testing within interval testing. Okay, well, in order to do interval testing on x squared minus 8x plus 5 is greater than or equal to 0, we have to know the zeros of x squared minus 8x plus 5. And in order to do that, we use the quadratic formula. And we end up with x equaling 4 plus or minus root 11. Okay, so with quadratic inequalities, we're going to use decimal approximations within our solution, but we're going to use exact values in our final answer. So x equaling 4 plus or minus root 11 is like saying x equals 0.7 or x equals 7.3. So the inequality x squared minus 8x plus 5 greater than or equal to 0 is roughly the same as the inequality x minus 0.7 times x minus 7.3 is greater than or equal to 0. And if you want proof of that, just check this out. If we do x minus 0.7 times x minus 7.3, we get x squared minus 7.3x minus 0.7x plus whatever you get when you multiply 0.7 times 7.3. Collecting your like terms, you get x squared minus 8x, and this number is roughly 5. So literally, what we're interval testing in this leftmost interval is that right there. So we build our number line with a 0.7 and a 7.3, and we test to the left of 0.7. We get a true statement. And again, if you're not sure what we're doing, take any number to the left of 0.7. Let's say let x be 0. And what we're doing is we're testing the statement x squared minus 8x plus 5 greater than or equal to 0. And when you let x equal 0, this statement is true. Now, pick a number in between 0.7 and 7.3. You could let x equal 4. If you were to let x equal 4, remember we're testing x minus 0.7 times x minus 7.3 is greater than or equal to 0. If you let x equal 4, that's a false statement. Or if you prefer, just plug it into the inequality, the quadratic that we're testing here, the quadratic inequality that we're testing within our leftmost interval here, and you would get a false statement. So we put an x there. And finally, if we let x be greater than 7.3, x squared minus 8x plus 5 is in fact greater than or equal to 0. We put a check mark there. So now what we do is we say, okay, we've finished our interval testing within this interval. Now, we have to take all values in the circled part that are less than 1, because remember, we're still in this overall question, we're still looking at values to the left of 1. Well, only the values to the left of 0.7 would be included. Values to the right of 7.3 would be way out here, but those are not part of the leftmost interval that we're in, so those are not part of our solution. Okay, now let's go into the middle portion. When 1's less than x less than 7, then x squared minus 8x plus 7 is less than 0. Don't believe me? Let x be 4. 4 squared minus 8 times 4 plus 7. 16 minus 32 plus 7 is negative 9. That's less than 0. So since x squared minus 8x plus 7 is less than 0, the absolute value of x squared minus 8x plus 7 is negative of x squared minus 8x plus 7. So solving this inequality becomes the same as solving this inequality. Well, this I can handle. We just subtract 2 from both sides, and now we've got a quadratic that's greater than or equal to 0. Let's multiply both sides of this by negative 1. I like to do that because I don't like having a negative lead coefficient like I have here. So if I multiply both sides by negative 1, I get x squared minus 8x plus 9. I still have a 0 on the right-hand side, but now I've changed the direction of that inequality. So this is what we've got written down here. Now we're going to remember, we're now going to do interval testing within an interval. So we're going to determine the zeros of x squared minus 8x plus 9. And the zeros using the quadratic formula are 4 plus or minus root 7. Well, 4 minus root 7 is 1.4. Roughly 4 plus root 7 is 6.6. So what we know that we're testing this within this interval between 1 and 7, we're interval testing x squared minus 8x plus 9 less than or equal to 0, which is roughly the same as this. So we can build a number line within this interval with zeros at 1.4 and 6.6. And now remember, what we're testing is x minus 1.4, x minus 6.6 is less than or equal to 0. That's what we're testing. Well, if I let x be less than 1.4, this is a negative factor, and this is a negative factor. When I multiply them, is it less than or equal to 0? No, it's not. So I'm going to put an x right there. Now, when I'm in between 1.4 and 6.6, remember what I'm testing within this interval is x minus 1.4, x minus 6.6 less than or equal to 0. So let x be a number less than, in between 1.4 and 6.6, say for instance 2. If I do that, I get a positive factor, but then I also get a negative factor. When I multiply them, is that less than or equal to 0? Yes, it is. So I'm going to put a check mark there. And then finally, when I go to the right of 6.6, testing this, I will get a couple of positive factors. Multiplying a positive times a positive is not less than or equal to 0, so I'll see that I'm going to get a x there. So what we want to do is we want to keep that part of the checked interval, the part between 1.4 and 6.6, we want to keep that part, but only if it's in between 1 and 7. Well, the entire interval between 1.4 and 6.6 is in fact in between our values of 1 and 7. So the valid interval that we got in this interval testing was valid within the interval it was in. So that's kind of confusing, but we get to keep it all. And finally, we go to the far right. When x is greater than 7, x squared minus 8x plus 7 is greater than 0. For instance, let x be 100. If you let x be 100, 100 squared minus 8 times 100 plus 7 is definitely greater than 0. So that means the absolute value of x squared minus 8x plus 7 is x squared minus 8x plus 7. So solving the inequality that we were given is equivalent to just solving x squared minus 8x plus 7 greater than or equal to 2, which is what we said here. Subtract 2 from both sides, and we get x squared minus 8x plus 5 is greater than or equal to 0. And we're going to do interval testing there. Now, believe it or not, this is actually, we're going to end up with the same results we had a while ago. We did the same interval testing in the leftmost column. But anyways, what we're going to end up testing is this right here. But we're testing it in the interval x greater than or equal to 7. So to set this up, we test a number less than 7. Again, remember we're testing x minus 0.7, x minus 7.3 greater than or equal to 0. Well, if I let x be a number less than 7, I have a couple of negative factors. It says positive times positive. It's actually a negative times a negative here. It's not positive times positive. It's negative times negative. So that, but it is true. Regardless, it's true. And then when x is in between 0.7 and 7.3, the testing that I'm doing is x minus 0.7 times x minus 7.3 greater than or equal to 0. When we do that, if I let x be a number in between there, say 4, I get a positive factor and a negative factor, and that being greater than 0 is false. And then when I let x be greater than 7.3, it's true. So now what I'm going to do is I'm going to take whatever's true about this that also meets the condition of x being greater than 7. Okay? So when we do that, I put 7.4 there. I should say 7.3. But this is the part that we're allowed to keep. This part is irrelevant because I'm not in an interval where values less than 0.7 can be part of my solution. Now, earlier I was, and so it's valid for that reason. But as of just looking at this interval testing here, the only part I'm keeping is right there. So now we can describe the shaded in set of numbers on our number line, and we could say x less than or equal to 0.7, 1.4 less than or equal to x less than or equal to 6.6, and x greater than or equal to 7.4. But we know better. We're going to use our actual valid answers that we got, the irrational numbers that we got using our quadratic formula, and we're going to state the answer that way with specificity.